In this example, I'm going to demonstrate how to calculate the velocity of sound in a tissue given the stiffness and density of the tissue. So if we look at, there's a formula for calculating that. The speed of propagation of sound in some type of material is the square root of the stiffness of the material given by the variable m divided by the density of that material using the variable rho. So for example, muscle tissue has a stiffness m equal to 2.670 times 10 to the 9th newtons per square meter. Okay, and you'll notice this is similar to the units of pressure. Okay, then it has a density. Muscle tissue has a density rho equal to 1080 kilograms per cubic meter. Okay, and if you have a density, and density is commonly, it should always be mass divided by volume, but you may find it in grams per cubic centimeter. In that case, you'll have to convert it to kilograms per cubic meter in order for the units to work out properly in this problem, which we'll see in a little bit. So I have my two values. I can then just set up my formula for the velocity of sound. C equals the square root of stiffness divided by density, and then plugging in my values for those two, I have 2.670 times 10 to the 9th newtons per square meter divided by 1080 kilograms per cubic meter. Okay, and now I could go right to the calculator and enter these values, but first I want to take a look at just the units in this problem. So if I look at the units in the numerator, I have newtons per square meter, but if I remember, a newton, F equals ma, is a kilogram meter per second squared. Okay, so that's just the newton part, but I still have meters squared on the bottom of this fraction. Okay, and then I'm dividing all of those units by kilograms per cubic meter. Okay, so if I just take a look at, if I work with these units first, I can see that while I could cancel the meter on top here by meters on the bottom, I could cancel my kilograms, and then I have meters cubed on the bottom of the fraction over here. So one way I can deal with that is to multiply this large fraction by meters cubed over meters cubed. So if I think of it that way, meters cubed divided by meters cubed, on the bottom the meter of that fraction and the denominator the meters cubed cancel, and on the top this is actually the same as meter cubed over 1, so one of these, this meter cancels one of the cubic meters up here, and I'm left with units of meters squared. So when I get done with all of this, the units under the radical are going to be meters squared per second squared. So I have my units. Now I'll plug in the numeric values here using a calculator. So the numbers are 2.670 times 10 to the 9th power divided by 1080. Enter. Yeah. So this comes out to be 2,472,000, and a few twos here, which we'll sort out later. So the square root of that and so when I take the square root, that's equal to 1,572 meters per second. So when I take the square root of the units, the squared term goes from meters squared per second squared to just meters per second. And so the velocity of sound and muscle is approximately 1,572 meters per second.